Hi, class. Last time we spoke about leptons. So far we've spoken about these two kind of particles, quarks and leptons. And if you remember, leptons are the electron and the neutrino. And the neutrino is so small they built this big detector on the South Pole to try to detect them. So the standard model tries to put all the particles together in a overall model, a concise model. And so the standard model includes the particles, the quarks and the leptons, as well as the forces that describe how things interact. So the strong force, the weak force, the electromagnetic force, and the gravitational force. And so the standard model looks a little bit like this. You've got quarks and leptons, and these are force carriers over here. We're not really going to talk about force carriers today. We just want to talk about why the standard model is structured this way. So let's talk about that. So the standard model is broken. It says all matter is comprised of quarks, and hadrons are basically combinations of quarks and leptons. Okay, so our quarks, and we spoke about how the up and down quark makes up protons and neutrons, and the first gen the leptons are comprised of the electron and the neutrino. Okay, and all those are here in this first column. Okay, we call this generation one. Okay, and that's really what all matter is made up of, that we see, we experience every day, right? The up and the down quark make our protons and neutrons. The electron is the electron, and atoms are made up of protons, neutrons, and electrons. And so everything that we experience in our day-to-day life is right here in this first column. Up and down quarks make up our protons and neutrons, and we have our electron. The neutrinos are so small we don't really experience them. They just go right through our body. They're out there, but we don't really experience them. Okay, so these four particles here, the quarks and the leptons, are really what we see and experience every day. So the question is, what are these things over here? What are these things in the second column, the charm quark and the strange quark, the muon and the muon neutrino, and in the third column, the top quark and the bottom quark, the tau and the tau neutrino? Well, if you look at if you look across each row, you'll notice that the up quark, the charm quark, and the top quark all have the same charge, plus 2/3. The down quark, the strange quark, and the bottom quark all have the same charge, minus 1/3. The electron, the muon, and the tau all have the same charge, -1, and the three neutrinos all have the same charge of 0. So they all seem to be similar in charge. And it turns out that these second column particles, what we call second generation particles, and these third column particles, or third generation particles, you could think of as really as just different versions of the first generation particles. So you could think of the charm as sort of a bigger version of the up quark, and the top quark is an even bigger version. So this is a larger version or more massive version of the charm, and the charm is a bigger version or more massive version of the up. Okay, so the up and the down are what we see every day. They make up our neutrons and protons. The charm you could think of as a bigger version of the up, and the top is an even bigger version still. Now these things don't exist. We don't see them in ordinary life. We do see them in particle accelerators and the CERN super collider. These things do exist, and so we consider them to be part of particles that do exist in nature, but they, generally speaking, don't exist for very long. So for very, very small fractions of a second, these second generation and third generation particles, we will see them in a super collider. but we don't really see them and experience them on a day-to-day basis. So these particles are part of the standard model, but there's something that we really don't, that they come into existence and then they disappear from existence pretty quickly. So they're not the type of particles that you're going to see on a day-to-day basis, but they are considered uh, uh, distinct particles that are different than the up and down quark and the electron and the neutrino. And so they are part of the standard model, but they don't exist for very long. They can be detected in supercolliders, but they don't exist for very long, so we don't see them and interact with them on a day-to-day basis. So the stuff that we see is in this first column here, this first generation stuff. The up and down quark makes up our protons and neutrons. Our electron is here, and the neutrino is here. This is the stuff that we see on a day-to-day basis. This stuff, the second generation and third generation, only exist in scientific. We see it in high energy experiments. Okay, and they say all matter is comprised of leptons. Leptons don't combine with and form other particles. So the electron is just the electron, the neutrino is just the neutrino, whereas quarks will combine. So three quarks will form can form a particle. For example, three quarks can form a proton, three quarks can form a neutron, and so we call basically combinations of quarks are called hadrons. So everything in the universe we say is made up of hadrons, which are combinations of quarks, or these leptons. And the model uh, is comprised of 12 particles overall, although these four here in the second column and these four here in the third column don't exist for very long, but they still do consider them to be part of the fundamental particles. So in summary, you'd say there are 12 fundamental particles overall. Okay. Um, Now, one last thing. There's a little note down here. It says for each particle, there is a corresponding antiparticle with a charge opposite that of its associated particle. So I just said that there's 12 particles, but really what I'm going to do is change that right now and say there's really 24 particles, because for each of these particles, for the up quark, there's a corresponding antiparticle. For the down quark, there's a corresponding antiparticle. For the electron, there's a corresponding antiparticle. For the electron neutrino, there's a corresponding antiparticle, and so on. For each of these, there's also a corresponding antiparticle. So the standard model says that there's 12 fundamental particles, 6 fundamental quarks, 6 fundamental leptons, and a corresponding antiparticle for each of these. So the 12 overall particles you could really think of as 24 fundamental particles. These 12 shown here, and a corresponding antiparticle for each one of them. Okay? All right, we'll talk more about the antiparticles next time. So in summary, the standard model. Each member of a generation has greater mass than the corresponding particles of lower generations. So as you go from an up quark to a charm quark, the charm quark has more mass. And as you go from a charm quark to a top quark, the top quark has more mass. Okay, so a top quark mass is greater than a charm quark mass, is greater than an up quark mass. And the same thing holds true for the other particles. A tau particle over here has more mass than a muon particle, which has more mass than an electron. The first generation charged particles do not decay. Hence, all ordinary matter is made up of such particles. Second and third generation charged particles decay quickly and are observed only in very high energy environments. So these second generation and third generation particles decay quickly, and so we only observe them in high energy environments. Quarks combine to form other things like protons and neutrons, so the quarks up here combine to form other things. Leptons don't combine, so our electron and our neutrino don't combine to form other types of particles. And for each particle, there's a corresponding antiparticle. So the antiparticle of the electron would be called a positron. The antiparticle of the up quark would be the anti-up quark. And so overall, we'd say that there's 6 quarks and 6 antiquarks, and there's 6 leptons and 6 antileptons. And so overall, there's 24 particles that make up everything in the universe. Okay, so I've attached, or you'll see a couple of 1 or 2 short videos to go along with this. So take a look at those 2 short videos and then answer the questions on the attached quiz form. All right, thank you.